Okay, thank you. This presentation is about property-directed reachability, which is a new algorithm from the verification community for symbolic analysis of reachability analysis of symbolically represented transition systems. You may also know it under the name of IC3, as it was devised by Aaron Bradley, the original author. But I like the descriptive name better, which was called one year later by Mishenko, Brighton, and Anne. And I will shortly tell you what I mean by symbolically represented transition system. But the point is that classical planning falls under this concept. And while IC3 or PDR has become a greatest hit of the last year in the verification community, I would like to also convince you that this is an algorithm worth studying from the planning perspective. The general characteristics is that it's built on top of a modern SAT solver, so it harnesses the power of SAT solvers. In which sense it is closely related to planning as SAT, but it combines explicit state generation with symbolic reachability analysis, and in this sense, it's also kind of related to explicit heuristic search. And yeah, let's have a look what it means from the planning perspective. So by symbolic transition system, please feel free to suggest maybe later on how you would call this thing. It's not a difficult concept, but yeah, I didn't find it explicitly stated anyway. So it's one of the minor contributions, I would say, that I formulated this way, the actual input of the algorithm. It's based on propositional logic, and you can easily translate planning tasks into this formalism. I would say the idea is that you take what encoding into planning as SAT does, but you just abstract away time so that you can put it back. But the algorithm, this algorithm does it in a kind of different way than SAT planners typically do. And yeah, so that's what I said. So you take basically any reasonable encoding of planning into SAT and combine it with PDR, you already have a planner. So you can start testing very fast. A little bit more details about what the symbolic transition system means. You have a bunch of propositional variables, sigma, propositional signature, and you have two propositional formulas over these variables, one for describing the initial set, one for describing the goal set. So here I'm a little bit generalizing in planning. This is already just one state, typically. And you describe the transition relation by a formula over two copies of these basic variables. So the second copy is the prime variables over here. And well, what is a state? State is a assignment to all these basic variables, and two states are related when if you take the second state, the successor state, and encode it over the prime variables, put them next to each other, this propositional evaluation satisfies the transition formula. Okay, how does the algorithm work? Abstractly speaking, it constructs a concrete path starting from the initial state, trying to go towards the goal. And at the same time, it maintains and refines some kind of reachability information. I will give a little bit more details later. This information is coming in the form of CNF, which means set of clauses. In fact, it's a sequence of sets of clauses, to be precise. And the path constructions work by either I succeed to go one step forward, or if I fail to extend the path, given the current reachability information, I somehow refine the information and learn a little bit more about the state space. The global perspective is as follows. The algorithm iterates over its estimate of what the shortest plan or shortest path through the state space would look like. So in this sense, it's kind of similar to what planning as satisfiability does. But there are two cool features of this algorithm. The one cool feature is that it can discover paths or plans of length L, which is greater than this current estimate. So it can sometimes avoid proving that short plans don't exist while actually finding a long plan fast. And why is this also cool is that this is just a one-line change in the algorithm, and if you switch this off, you end up with optimal planning. And the second cool feature is that after each of those major iterations, there is a special check which checks for some kind of convergence in the reachability information, and the algorithm is basically guaranteed to discover that no plan exists, kind of unlike what planning satisfiability is able to do without any additional tricks. This somewhat tries to describe the data structures inside the algorithm during second iteration. You see that, well, this is the set of initial states, and currently we have the sequence of reachable, which defines the reachability information has 3 elements. Those are those 3 regions, L2, L1, and L0. They are, as you can see, they are ordered by inclusion, and yeah, L0 is always described precisely what the goal should look like, whereas the other layers, as I call them, they are over-approximating the set of states that would reach the goal in k steps. So this is maybe there are states that can reach the goal in 2 steps are somewhere here, and this is my current over-approximation. So as long as there is a state which satisfies the latest layer and is also an initial state, I pick that state using a SAT solver, and I try to look for a successor which satisfies the next set closer to the goal. And this either succeeds or it fails, in which case I do some refinement. Before I return to the picture to explain it in more detail, let me say precisely what it means. So, as I said, the basic operation, how the path is being constructed, is either I find an assignment, either I find a successor state, which satisfies some kind of set of clauses, propositional clauses, and then in the SAT solver, in the propositional language, you can express it by like this. Or what the algorithm requires from the SAT solver, which is something which is easily implementable, and the more SAT solvers give you this, but it's a little bit more than just saying yes or no. I require that the SAT solver gives me a subset of those literals which have been supplied into the query that already suffice to show unsatisfiability of the query. What it means in the picture is that if I discover that this state T doesn't have a successor, immediate successor that will be a goal state, I will take this subset describing subset of literals which describe the state T, and I'll call it a reason, and this reason describes larger set of states which all share the property that they cannot reach goal in 1 step. I negate the reason. You can consider the negation of the reason as the region outside of this rectangle. And I conjoin this clause, which is the negation of the set of literals understood conjunctively. I conjoin it with L1. This way, I kind of carve out this region, which has now been shown to lie at least 2 steps away from the goal, and I refine L1. Yeah, this is how it works in a nutshell. And yeah, the second half of this slide is dedicated to the main theoretical contribution of the paper, and it is the following statement or claim. Actually, what I show is that even it seems that the SAT solver is quite important in this algorithm, and it indeed is in general. In planning specifically, in the strips formalism, you actually don't need a SAT solver to compute or to conform with this contract, which is the only thing which the SAT solver is required to do inside the algorithm when you treat it as a black box. And that can be explained quite simply because, I mean, I'm looking for a successor state which satisfies some additional property. I can just iterate over all the actions, checks whether any of them is applicable in the state, and then check whether the successor satisfies the set of clauses. That's the easy part. The non-trivial part is if this is not the case, and I'm supposed to compute the reason for the failure. And because the efficiency of the algorithm relies heavily on how small this reason is, I'm trying to minimize it, which means that I'm trying to generalize from the failure to extend S. I have to do some optimization step and extract a reason which is good enough. But this is possible, and it can be done in time polynomial with respect to the number of actions, the size of the state, and the number of clauses in this set, which is only growing slowly throughout the computation. I've performed some experiments, and the major findings are the following. So this algorithm, the Satzolver-free version has been implemented, and I also tested a couple of encodings which took the problem and turned that into STS, and then I ran the PDR I've developed as abstract model checker. And it turned out that this Satzolver-free variant is more efficient. So then I continued just testing the Satzolver-free planner, which is called PDR. I've discovered that progression in this setting is more successful than regression, which is kind of contrary to what the experience from model checking is, but this can be explained by the fact that in model checking they are using this algorithm mainly to find unsatisfiable instances or unsolvable instances, which means that the system is bug-free, whereas here we are interested in finding plans. I'll skip this one, and yeah, there are some numbers and some statistics about domains. You can see that there is still something like 100 problems with respect to coverage from 1,500 in total, which is all the strips problems I could collect from the IPCs. But the system seems to be outperforming MP, which I consider one of the best planner S satisfiability currently available. And there are also some domains where out of those 4, PDR plan solved the most. To conclude, there is a new cool algorithm for a reachability analysis of symbolic represented transition system. You can combine it with any encoding out of the box, but you can also do some tricks, exploit the structure of the planning state spaces, and get something even more efficient. And there are some other cool things in the paper, such as the realization that this algorithm is kind of related to graph plan, which is a little bit surprising maybe. Yeah, one of ideas for future work is to think how this could be extended and lifted from the grounded setting of propositional logic to first order. Thank you.
So we have time for a quick question.
So first of all, let me advertise the paper again. It's really marvelous, and everybody here should read it, I think. So I'm really interested in what you mentioned here on the related work, because your approach seems in some way to be a hybrid of a symbolic search and like an explicit state heuristic search. So for example, I guess you could initialize your layers with any kind of lower bound as long as you could encode it nicely as clauses. So do you think something this direction could be another promising research direction, or I guess it's an open question. Like can we exploit these directions or these relations to other planning algorithms in certain ways? Do you see some promising things that could be done there?
Yes. So there are some specific properties which are named in the papers, which those layers or the reachability information pieces need to satisfy. But then this is all that is needed to show that the algorithm is correct. So I didn't think about it, but initializing it with some kind of information extracted from admissible heuristics would probably work. And yeah, it's an interesting idea, but I didn't think about it too much yet.
All right, so let's thank the speaker again. And the last